dynamical systems tutorial. The slides are a little bit different from when I uploaded, but almost the same. So here's what we're going to do. So it starts softly. We'll first talk a little bit about what a dynamical system is, very simply. And I'll insist on one fundamental property of dynamical systems. That's the main thing. And then I give you a little bit of a survey over the mathematical realizations or implementations of dynamical systems. And that's relevant because we'll do these dynamical neural fields, which are not just conventional differential equations. And then come these more advanced concepts, the fixed points and attractors, bifurcations, the Hopf theorem. And I'll end very briefly on the difference between forwards and inverse dynamics, just 2 slides, but that all builds to that. This stuff here at the bottom, these 2 points are called sometimes the qualitative theory of dynamical systems. I'll also recommend some books as we go and point to resources that we have here. And so you could assume that sort of from this point on, even those who are mathematically skilled might find these things a little bit new, depending on your background. Okay, so what's a dynamical system? What is dynamics? The word comes from Greek force, and it's ultimately about causes of movement. You know, daily life, colloquially, people use it very generally. They say, "Oh, a very dynamic personality," right? Or they say, "Oh, these are very dynamic, I don't know, stock exchange numbers," and they mean by that just time varying. And sometimes, as you might know, one even uses the word dynamic in the sense of the range of something, like the dynamic. A piece of music is very dynamic in the sense of very loud, very low volume. So the range in which something varies. But the more exact term, both in terms of the history of the word and the mathematical background, is that it's an account for time varying things that is introducing some notion of causality, something that causes the time variation, accounts for the movement. That's what a dynamical system is. And that's a very general idea. So you could say that in all fields of science, of engineering, but also actually extending into economics, and there's even a field called quantitative sociology. So all the fields where people use math, dynamical systems is one of 2 major frameworks that are used. So almost everything mathematically described is using notions of dynamical systems. The other thing is stochastics. So probability theory has, it's often misunderstood. Statistics is actually something very specific, but the theory of what chance means, probability means, is another important branch that is used everywhere. And actually the 2 are married when we're talking about stochastic processes, that is time-varying systems in which there is some element of stochasticity. And we actually, technically speaking, are using in this course stochastic dynamical systems, so-called stochastic differential equations. But I'm actually not explaining that mathematically. I'm just alluding to that, and the underlying methods a little bit more advanced. So it's worthwhile having a good intuition for dynamical systems. And this is why those of you who have degrees in or study engineering or physics will be very familiar with these concepts. Computer scientists are sort of on the edge. In applied computer science in Bochum, there is some continuum math that includes some dynamical systems. In more conventional computer science programs, there isn't actually a lot of continuum math, and therefore also not a lot of dynamical systems. Okay, so what is, let's make that more concrete. So time variation and its causes. So here, I'm talking about dynamical variable, x, this is position, and it varies in time. This will be a time variation, right? And so it grows here in time. Let's say this position, you're walking along a corridor, and therefore your position along that corridor, that will be one-dimensional position along the corridor, changes in time. You're moving to, I don't know, the north side of it, depending on how you span that axis. And then your rate of change of position will be your walking velocity, right? Your speed. It's denoted dx by dt, or sometimes also x dot, or you give it a new letter, velocity. And so if you have a linear change of your position in time, the rate of change is a constant. That will be the slope of this curve against time. And that constant velocity would be your walking speed. right? So that's just time variation. Now, here's a sort of a pseudo derivation of a dynamical system using exponential time courses. So here, let's assume we have some variable that decays exponentially like that. And let's look at the derivative. So this is the rate of change, x dot. I'm using the notation that we use in the applied fields and physics most often, x dot. What would that be? So it's decreasing, so the rate of change is negative, and it's quite negative here. I'm using the symbols to look at matching points in time. So it's a negative number, and then the slope gets a little shallower. So it's a negative number, but not quite as negative. And that gets even more shallow. And so you see ultimately it becomes flat, so the slope goes to zero. So it's always negative. It's a decreasing exponential, decrease. And ultimately it peters out. And so both the value goes to zero and the rate of change goes to zero. Now, if you were to look at the correlation between x and x dot, you would find out they lie on a straight line. So let's take here this rightmost point. We have a not very large value of x and not very large value of x dot. That's negative. So that's where these two lie. And then for this moment in time, you have more negative and more positive for x and so on. And if you do that quantitatively, you find they lie on a straight line. And it actually turns out, so that what I've plotted here is actually a dynamical system. It's a special case of a dynamic system where the rate of change of some variable is a function of that variable. And that function is here a linear function, this negative line. And this will be actually the dynamical system we'll be looking at a lot, the dynamical system that has a negative slope that will lead to attractors, and that will lead to exponential solutions, and we'll study that. The exercise sheet I will be uploading today will invite you to study exactly this dynamic system, the linear dynamic system with a stable fixed point. We'll get to that. This is the more general picture of that. We often write a rate here on the left, or you could divide by that and on the right. And in the exercise sheet, I'm inviting you to understand what that means. So if I divide by that tau, then the slope here of this function is not -1 as it is now, but it will be 1 over tau. So you can vary the slope by varying tau. And the reason for that is that the solution has this shape. So if you take this dynamic system here and solve it, then you find it has an exponential time course, and you divide the time by tau. And so this is something you can check, and the exercise sheet will invite you to actually check that. And then, the kind of solutions we have here are these exponential time courses. Exponential time courses are very fundamental in all of the application of dynamical systems, and they are the solutions of linear dynamic systems, and linear dynamic systems are very important. You will see this in the course of the lecture, why they are so important. And they are actually the time courses that have time scales. So people often talk about time scale in a loose way. They say, the time scale of, I don't know, of weeks versus years, or of a century versus a decade, and so on. That's loose talk. Mathematically speaking, time scale refers to exponential time courses. And the notion is that if you have an exponential time course, there is a particular time that's called here tau, on which the time course makes a significant change. Here, by convention, we are talking about e, the natural number, which is the basis for the exponential function, 2.7 something, let's say approximately 3. And then if you insert t equals tau, you get exponential minus tau over tau, exponential -1, so 1 over e, and that will be about a third of the initial value. So the time it takes to decay to about a third of the initial value, that's the time tau. And that's a universal scale because it doesn't matter on what level this initial value is. So if you, for instance, ask, when does this value after time tau decay to another 1 over e, so a third of this, so 1 over 9, that takes, again, the same time tau. So after 2 tau, you have 1 over e squared, right? And so it doesn't matter what your x of naught is, it always takes the same amount of time to reduce the distance to the final value by the same factor, the factor of e here. The same is true for exponential growth. There, it's just a question, how much time does it take to multiply your distance from the terminal value by a factor of e. So that's not the case if you have other kind of time courses that look like that. For instance, if you have 1 over t, then it takes different amounts of time to reduce the distance to the asymptotic value by a certain percentage. So you can't actually talk universally about the timescale without knowing what the actual numbers are. It's only exponential time courses that have that property. You might know from high school or from popular science the idea of exponential of population explosion. If you think in discrete times, for instance, you have some bacteria and they, let's say, split every 10 minutes, and then you can say that the population will explode exponentially, and the doubling time will be exactly those 10 minutes, independently of how many bacteria there are already in the population. That will be an example of a time scale. So that's quite important. We'll be often talking about time scales. So this linear dynamical system, a nonlinear dynamical system would be just any function. So the rate of change is just any function of x, but it is a function of x that is given an initial value of that variable. The rate of change is well defined. So in the math quiz, I asked you if a function, for instance, that was a vertical s is a function. It's not a function because there is actually no unique value delivered for any value of the argument, and that would be then also not a dynamical system. So this would be called a nonlinear dynamical system. You see, a linear dynamical system doesn't have linear time courses as solutions, right? The linear dynamical system has exponential solutions. Those are sort of the building blocks of dynamical systems. A dynamical system like we looked, this is actually also a dynamical system. You can actually say the rate of change is a position of function of x, namely the trivial function where it is constant. And that is the special case where you get, when you have a constant rate of change, right, you get a linear solution in time. That is a very unusual solution we will not often be looking at. Okay, now the fundamental property of dynamic systems already hinted at, and mathematically it is sometimes called the existence and uniqueness theorem, and it essentially says that in a dynamic system, if you know this function that characterizes the dynamic system, how the rate of change depends on the value of your variable, then the future is predicted by just knowing one initial value. Initial value of this variable, for instance, here, and then you can say the future is uniquely determined by that. You can also predict the past. Doesn't really matter which direction of time you go. This requires some mathematical things. It requires that the function f is sufficiently smooth, and strictly speaking, is only in a finite interval of time and so on. But the kind of dynamical systems we look at are very soft and smooth and so on. So for them, all these technical limitations are never an issue. I often like to make people think about this as a form of mental simulation. So for instance, here, if you have that dynamical system, you see that there will be, if this is your initial value, you can look up the rate of change. It will be a negative rate of change. Negative rate of change means that x will decrease. So decrease will mean moving to the left. So a little later, you have, again, a negative rate of change. So still go to the left and so on. And we'll be thinking about these kind of mental simulations a lot in this tutorial and generally in the lecture course. Yeah, that's the fundamental property of dynamical systems. This is how dynamical systems explain time courses rather than just describe them. They say, if I have the right variable, and that might mean a vector or multiple variables, we'll come to that, then just knowing a value of that variable will determine the entire time course. So it's a very strong condensation of the time course. You could say there are infinitely or continuously many time courses, namely time courses that are predicted from any initial condition. And all of those are condensed into this one function, the function that determines the dynamical system. Now, this is a very, that's what we call it a law of motion. It's very strong condensation or compression of data. So here to state the same thing a bit more formally, this variable is sometimes called the state variable. It spans the state space. So X would be just, a special case would be X is a real number. It could be a vector. You can look at high-dimensional things in a moment. And they're always called state space. Physicists call that sometimes phase space, which has some history. Why it's called that? It's a bit confusing because phase has many different meanings. So I'll try to avoid that term just for you to connect to that knowledge. But it's more commonly called state space. And this function f of x, that's on the left side, on the right side of the equation, is often loosely called dynamics, the dynamics of x. This is sort of jargon. And I'll use that jargon. I'll say plot the dynamics, and it means plot that function f of x. So plot, in other words, x dot or dx by dt as a function of x, which is a function, that function f of x, the dynamics. A little later, we'll see it's sometimes also called vector field, and we'll see why it's called a vector field. A time course x, that x of t, that is obeys the equation, so has is a solution in the sense that when you compute the derivative is equal to that f of x relative to some initial conditions that are called here x naught. That's called a solution of the dynamical system. Kind of obvious. So what I just hinted, again summarized, is the special case where dynamical system is a differential equation in one dimension, then the initial value of that one dimension variable determines the future. Now, I want to next just show you that there are a couple of other mathematical framings of dynamic systems. And one of those we will actually use in the course. So first, let's think about many such variables. So we summarize them into a vector then. So we have, let's say, n variables. And here just the boldface means this many variables. So these many variables have many rates of change, right? So this is a vector with x1 dot, x2 dot, and so on. That's the vector of the rate of change. And now a so-called system of differential equations is then a dynamical system. And this function, importantly, depends on the whole vector. So it's different from just writing down n one-dimensional differential equations where, for instance, x1 dot would be a function of just x1, and then x2 dot would be just a function of x2, and so on. No, here, the rate of change of x1 could depend on all the other variables as well, on the entire vector. And when that's the case, we'll actually talk about coupling, that these different dynamical systems are coupled. That is, the time courses of x1 will also depend on the initial condition of x2, x3, x4, and so on, right? So that's systems of dynamical systems. Very naturally have those. A more radical case is that there would be continuously many variables, not just a discrete number, but continuously many. So for instance, I would have a variable x, a family of variables x that depend on y. You might be familiar with that from physics, for instance, electrical field, magnetic field, and other fields, quantum mechanics. The complex fields are variables that depend on space, for instance, and that there will be a continuous set of state variables. In physics, often then x is also a vector, so there are multiple variables, discrete multiple variables, like 3 variables, and each one continuously many. But we will look at scalar fields, so x is just one real number, but there are continuously many of those as a function of y. And then y can be in a space of different dimensions, and we'll actually have that. So in physics, you have then partial differential equations. So these are equations where the rate of change of this whole family of variables depends on the variable, but it might also depend on the spatial derivative of that variable, spatial if y is space. So on how strongly the values of this variable differ in neighboring locations along that space. So we will not actually be typically treating that. I'm just pointing that out to connect to knowledge that you might have. These partial differential equations are, for instance, the Maxwell equation and the Schrödinger equation and other equations like that, all the field equations of physics. We will also be looking at field equations, namely at, with the same object, that is that there is some variable, we'll actually later call it u, that depends continuously on some space here represented by y, but they will be so-called integral differential equations. That is, the rate of change of these entire continuous family of equations will depend not on the derivative, but on an integral over these other variables and the variable itself. So it might depend explicitly on these extra variables and on the equation, the field variables integrated over this hidden dimension. So integrated, let's say, over space, over space, where if you think of y as being space. This might sound a bit abstract now, but you will later see it makes a lot of intuitive sense when we do that. So in both of these cases, your initial value isn't just a discrete number of values for different x's. It's a whole function. You have an initial function x of y. And if you think of this electrical field, then your initial value would be the electrical field distributed over space. And then you would have to see how it evolves in time. So this gets much more higher dimension, much more complex. So that we then talk about how many dimensions does y have. Y could just span a line. It could be the Maxwell equation would be three-dimensional space. So y is a three-dimensional vector. And for each vector, you would have, if this is the electric potential, maybe just one variable, or you could even have more variables. Good. There are some more exotic dynamic systems we will not be using here, but I point this out because you will find this in in textbooks of neurophysics, the sort of computational neuroscience textbooks that I'm not following, but occasionally we'll be referencing those. And those are a little odd in a way. Sometimes they're called delay differential equations, and they are so-called functional differential equations. So I just mentioned that again to connect to that. So in neural models, this happens sometimes because you're keeping track of the activation, for instance, membrane potential in neurons, and the synapse connection between the different neurons introduces some special mechanism through which the electric potential in a neuron is changed by spiking activity in a presynaptic neuron, a neuron that couples into that neuron. And that synaptic transmission takes some amount of time that isn't covered by these equations they're looking at. And so they model it by a delay, for instance, about 1 or 2 milliseconds. And so what that means is it's a dynamic system where the rate of change at a time t depends not on the variable at that same time t, but at a variable some distance in the past, that delay equation. That leads to all kinds of mathematical complications, and we'll not really study that here. The functional differential equations are just a continuous generalization of that. So here, the rate of change depends not on the value at just one moment in the past, but on a whole interval in the past. So maybe has some lower bound, but the integral over t prime would cover all times that up to time t, the time t we're looking at here. This is sort of a more extreme kind of delay differential equation. So in physics and most engineering, these kind of equations are not so common because in physics we would always think that there has to be some other state variable that represents those values in that past or in this interval. There's got to be some physical matter that transmits these states. So in a way, these delay equations only come about because we eliminate those variables from description. So for instance, in the neural case, the synapse has its own properties. There are some state variables that describe the state of the synapse. And when I describe that, then I don't need to make that jump. I could actually represent all the intermediate values as being represented by the state of the synapse. And in engineering, sometimes people use these kind of equations because they something like a filter that stores past values. Right? If you implement this on a computer, you need to store the intermediate values, right? And physically, that would be another state variable, but it can sometimes happen that it is useful to eliminate that. So we're not doing that, but I'm just trying to connect to stuff you might know. Good. From a mathematical point of view, the dynamic systems don't necessarily have to be in continuous time. You could also just think of discrete time. So like on a computer where you have a clock and you update the clock, and so time would be an index n that increases, and the dynamical system is then simply an iteration equation where the new value of a variable is a function of the just past value, the recent value. If it depends on a couple of iteration steps, you can just make the variable x a vector which contains a couple of past values, as long as it's just a discrete, a limited reach into the past that you need. It turns out that dynamical systems in discrete time and dynamical systems in continuous time have a close relationship to each other. In fact, you can take any continuous time dynamical system and make it a uniquely, well, in some qualitative sense, well, complicated, but topologically equivalent discrete time dynamical system. That's the Poincare theorem, which I'll not explain here. And you can take a discrete time dynamical system and make it a continuous time dynamical system. It's not unique, but it is actually, there is some one-to-one relationship. And for that, we need the qualitative theory of differential equations. I'm not going to explain that now. But there is a very close relationship between these two. The textbook that I like to recommend is by Scheinemann. Actually, has this feature that it studies both continuous and discrete time dynamical systems. It's a wonderful book. I really love that book, and Scheinemann made it free. So he just sent him a postcard, and this is the link. You have these slides. You can look up that link. It's just changed. I think the book is going to be re-edited, but he still offers the old version for free. I really find that very generous of him. So look it up. It's a very useful book, especially for beginners. It turns out, just say that for your warning, that if you look at discrete time dynamics, it's actually more complicated than continuous time dynamics, in the sense the solutions can be more complex more quickly. Some of you might know chaos theory, and chaotic solutions arise even in a discrete time dynamical system with just one variable. Well, if you want to look at comparably complex solutions for continuous time, you need at least 3 dynamical variables and a lot more conditions. So you could say, yeah, I'll say more about that later. So we're not actually using discrete time in that sense in our models, so continuous time. Sometimes you will find people using these kind of iteration equations for recurrent neural networks. They will say, oh, the new value is just the past value with some inputs. And that is not a good characterization of neurodynamics because there isn't, in the brain, there isn't a clock that sort of updates on the neurons. So the spikes occur at discrete times, but these discrete times are distributed continuously. They're not like a clock time. The spikes occur at any moment in time, and therefore they actually sample continuous time. So this is really just because people are, I'll show you in a moment what it means to solve a differential equation numerically, and they're taking essentially the numerical solution as the formulation of the dynamical system, but it's actually not theoretically very clear. Good. And here I mentioned that. So in numerically solving differential equations, that's what we do all the time. We actually solve things on the computer. We rarely ever really analytically solve anything in practice. And this is the difference to learning dynamical systems as a mathematical toolbox where you're solving equations. That's not what we're doing here, and that's actually not what is done for most applications of dynamical systems. Usually it's done on the computer. And on the computer, of course, time, it's always approximate in discrete time. There's a clock, and the clock counts through time. And therefore, the notion is that if you do these with sufficiently small time steps, then it approximates the continuous time solution. So this is based on, ultimately on the Euler, the so-called forward Euler solution, even though that is a very bad numerical procedure, but it's sort of conceptually makes it understandable. So in the Euler idea, it goes back to this Leonhard Euler. The idea is that you just take your continuous time and sample it by having one value every delta time. Delta time would be your time step. That's the computer clock time step, let's say, if you do it in the extreme case, or you define it in some way in your code. So to get the ith time value, that will be I times that time step. So instead of x of ti, we write xi for having these variables at these discrete times. And then if you intuitively think about that, the rate of change, also written sometimes as dx by dt, is approximated by delta x, so the change of x from next time to the previous time, divided by that time step. So if the delta t is small, it's an approximation of that. And let's say that's the case, then we would replace here the left side by dx by dt. We put the dx, the delta t to the right side, so it will be multiplied here this f with the delta x, and then we add this xi to the right side. And so the next value would be the previous value plus the change, the function with the delta t as a time step. And so if delta t is very small, this is a discrete time approximation of the underlying differential equation. You see, this is sort of like the discrete time dynamical system, except that there we called the whole right-hand side the function g, and here it is linear function plus f. And in fact, if you look up in Chinaman, then all the dynamical systems properties differ exactly that way. That is, for instance, where for f, a fixed point will be where f is 0. For that function g, a fixed point will be where g is equal to x. Now, because f is 0, then g has this x in here. So that's conceptually a bit how you go from discrete time to continuous time. And so when I said some neural network folks are using this, they're using this in this sense. They write down this equation for the neural network, and this would be from the neural network some values. And so that's really just numerically approximating a continuous time dynamic system. So this particular approximation is not a very good one, in the sense you need a really small delta t to make this work, even though it is still used. And in fact, in some of our numerics, we use it, and that has certain reasons. For instance, when you have stochastic systems, and also when you have systems where the function f depends on some sensor data that come in, and then it's easier to do it this way. While normally modern numerics uses much better methods. The very classical is so-called homokuta. It's actually a typo, should be kuta with an A here, sorry. So that scales much better. And actually all the numeric procedures you can get automatically from MATLAB and things like that. They have so-called adaptive step size. So they always optimize something. Again, that can be done when you have noise. These are not actually good approximations. I won't go into that because I don't think that's what we need, but we'll later be using simulators that inside use stuff like that. Yeah. So again, just say this here for you to position yourself relative to these things. It's not like you have to learn all the details of that. I was not going to run through the code here. Okay, so that's the elementary part. And now it gets a little more adventurous. Any questions up to this point? Maybe not. Good. So now I'll go to discuss attractors, repellers, and bifurcations. So on. This is sometimes called the qualitative theory of dynamic systems as compared to quantitative. Quantitative is really solving equations and sort of the typical thing you do in calculus to solve equations. While qualitative theory is about the flow. I'll talk about that in a little bit. It's a very nice textbook. I personally really like Lawrence Perko. The 4th edition was in 2001. I don't know if there's a new one. That's a very advanced book, actually. But it is quite readable, and there you will find the qualitative theory is like in chapter 4 or 5, so it's really far back in the book, so you can get a sense that we're doing something advanced. Of course, we're not really proving things and not really, using the methods. We're just using the results of that. So, so what's the qualitative theory about? In the end, you'll understand why we do this when I talk about inverse dynamics, not about modeling. But for now, just take it as given. And so what we want to do in the qualitative theory of dynamical systems is we want to look at all solutions, the ensemble of the solutions. And by all solutions, I mean give for all initial conditions. In fact, the flow is the hypothetical mapping from the whole space. If you take any value of the state variable, is it a vector or function, whatever it is to take all possible initial conditions as a space, and then you are saying from all those initial conditions, what's the future? So you get a mapping from that entire space to that same space again for every moment in time. So it's a continuous family of mappings. That's sometimes called the flow. And so the interesting thing is to say then, these ensemble of all solutions, do they have certain properties? Ultimately, can I say that two dynamical systems are sort of the same because their ensemble of solutions is very similar? So for instance, you can think the flow of the ensemble of all solutions is just a little bit deformed. For instance, if I take one of those dynamical systems here, let's say even this one here, and I'm now, instead of a straight line, I make it a little more wiggly. Then the solutions they always look exponential. It doesn't really matter where you start. And if I deform it from a straight line, maybe these functions will also just deform a little bit. But qualitatively, it's still very much the same. You could sort of make a one-to-one mapping. That's the notion of topological equivalence. And when we look at the flow, we're really more interested in qualitative differences where the flow really changes qualitatively and not exactly what the flow is. And you can see how that might be useful when we're modeling the behavior of a nervous system or models of behavior, because we can never be sure we have exactly the right equation. We're just saying, well, it's this class of equation that has certain properties of the solutions, and that's where we're driving at. And the way that we do that is by looking at so-called invariant solutions, and I'll give a more precise meaning to that in a moment. That's really used based on fixed points here. Mathematically, there's more than that, but we'll be primarily using fixed points, and then they're so-called stable and unstable manifolds. So let's make this concrete here for this very simple example. Remember, this is the nonlinear dynamic system, this red line that we discussed earlier. And now I'm looking at the intersection here with the x-axis, where the rate of change is 0. This is sometimes called a fixed point. So a fixed point means it's a solution of f of x equals 0. The rate of change is 0 at the fixed point, right? And that is a solution of the dynamical system, right? It's a special solution because let's say, if you start with that value, your rate of change is 0, so you will just stay in that value, right? So it's a constant solution, constant in time. And if you start, meaning once you're in that solution, you stay in that solution, right? So that's called a fixed point. And now this fixed point is an attractor. And to make it intuitive, what that means, let's say we start anywhere to the right of it, has a negative rate of change, right? And by that logic I previously hinted at, we could say, well, that means it's going to decrease here, the value of x. So I would be moving here to the left until approaches very much, and then ultimately the rate of change goes to 0. The length of this vector and how quickly it moves to the left will become smaller and smaller as the rate of change becomes smaller, and ultimately I will approach that time invariant solution. And similarly, if I'm to the left, I have a positive rate of change, so it will grow, and I can approach this fixed point, ultimately get stuck in that. And that's where the notion of attractor comes from. I'll define it more formally in a moment. But it essentially means that if you start somewhere in the vicinity of the fixed point, you're going to converge in time to the fixed point. Now we call it a fixed point attractor. The generalization is other kind of invariant solution, and you can have an attractor for those. For instance, periodic solutions would be then a so-called limit cycle attractor, and you can have so-called chaotic solutions that will be sometimes called the strange attractor. So mathematically, it's really just, the fixed point is really just the constant solution. So you look at this equation, x dot equals 0. You have to determine the 0 of f. And so that's where the function crosses 0 in one dimension. What we call stability here to define the attractor is what mathematicians actually call asymptotic stability. So asymptotic stability means there is an environment. It's actually more precisely that there is an environment which can be a small environment interval around the fixed point, such that any value within that set, when you start from that value, you converge in time to the fixed point. So it attracts, right? That's where the word attractor comes from. Stability is actually slightly different in mathematics, but the non-mathematicians, like the physics, engineering types, we all call asymptotic stability, we just loosely say that's stable stability. Even though mathematically, stability is a little bit different. Stability really just means that if you start near the fixed point, then you stay near the fixed point, but you don't have to converge to the fixed point. And that's important because when we say that a fixed point is unstable, we mean it is not stable in this mathematical sense. We don't mean it's not asymptotically stable. You know, if you don't converge, you can still stay near the fixed point. So when we say unstable, and we really mean that there are arbitrarily close to the fixed point, there are initial values which move away, which diverge, where the distance grows beyond any bound. This history, why this subtlety, it really has to do with ultimately with physics. You will know that well, maybe some of you know that in physics we have conservation of energy. And these conservation laws make that under some circumstances, there are no attractors. This is called Liouville's theorem, for those who know these sort of things. Liouville's theorem, that means that the volume of phase space stays constant. That is, if you have a set of initial conditions that is a whole interval or some volume in 3D, a little cube, let's say, and you look at the history, the time course of that set of initial conditions, the volume, the length of the interval or whatever it is, it stays constant in time, and that's due to energy conservation. And things like that cannot have attractors, but they will have stability. For instance, when you look at the planetary orbits, then we're expecting them to be stable. That is, the Earth is expected to not move very far from where it currently goes around the sun. We hope it doesn't fly off someday and go somewhere else, even though there is some mathematical doubt about that. And that is a case that's not captured by asymptotic stability. So, but we don't really need that. I just say that to clarify, because you will see that in the more mathematical text, there's this difference between asymptotic and real stability. So we're using loosely the term stability to mean asymptotic stability, and that means attraction. And then we'll say unstable, that will occur quite a bit. And then we mean by that really diverging in some direction. Good. So if you have a attractor, a fixed point attractor, this red line is a nonlinear dynamical system, and what I was saying earlier could be, doesn't have to be straight, but you can see that I could approximate it linearly by a function that has the same slope at the fixed point, and then starts to deviate. And a nonlinearity like that, where the linear function is really just is a good approximation near the fixed point, that's something we would call non-essential nonlinearity. Physicists call this a perturbative nonlinearity. And what that means is that when you are this attractor, or a fixed point attractor, and that means ultimately you will be converging to this attractor. And when you're close enough, the linear description really very much describes all the behavior. And that is why linear systems are so important, because almost all the systems we're building in technology or we're able to observe in nature over longer timescales have stable states. If not, we wouldn't observe them, or they wouldn't be useful. And when they have stable states, again, in the sense of asymptotic stability, then once we're close to the state, they can be linearized, and then the linear system describes quite well that system. And that's why the exponential time courses are so important, because once it's linearized, the solutions are all exponential, and that we can characterize things by that. So that's the motivation why now I look at linear systems to characterize stability. Later we'll see then that nonlinearity also plays an important role. So if I have a linear system, I just argued intuitively that it's the slope of the dynamics at the fixed point determines the stability. You made this mental simulation a couple of times. For some bizarre reason, I changed the variable to lambda on this slide. I think I stopped doing that in a couple of slides. I apologize. I have another version where that's x, but apparently in my current slide deck, I have these old slides where I use lambda as the variable. I don't know why I did that. So yeah, when the slope is negative, it's stable, and when the slope is positive, it's unstable. And if you're to the right, positive rate of change, you're going even further away. If you're to the left, negative rate of change, decreasing even more. And so here the fixed point divides these two directions where the there is a divergence either to the right or the left. You get away from fixed point. In any case, it's actually called a repeller, a fixed point like that, because it repels any initial condition that's not exactly the fixed point. Here you can maybe get a first sense for the flow and qualitatively different flow. You could say this dynamical system and even this one, they all have the same qualitative flow. That is, it's all converging along the horizontal axis to this fixed point. Just the exact rate of how it converges might be a bit different for the nonlinear versus the linear one. While here, you would have a flow where there's a dividing line, everything flows to the one side and everything flows to the other side. And these two are really qualitatively different. There wouldn't be a way of how you could sort of elastically deform one flow and transform it into the other. You would have to make a cut and really separate things. And that's how these would be two dynamical systems, this one and that one, that are qualitatively different. They are not just a little deformed versions of each other. That's where qualitative theory of dynamical systems comes in. So we will be attending very much to the stability. These differ. The fixed point here differs by stability, and when the stability changes this way, that will be a significant change in the dynamical system that we will take seriously. I'll have to explain more about that in a moment. So if the slope is zero, like this initial example we had of walking, right, where the rate of change was actually, it wasn't zero, it was just a constant. It's not exactly the same, so I forget that. So if the slope is zero, then you have continuously many fixed points. Every point is a fixed point. It's not really asymptotically stable, because if you start in the vicinity of a fixed point like here, then you just stay there. You don't get attracted. So it would be stable in this mathematical sense because you're not going away, but not asymptotically stable. It wouldn't be attractive, right? You think of a table and you have a ball. Let's say you might need some friction, so like a sticky ball on the table, and you put it in any place, it would be a fixed point everywhere, but it would not be an attractor because you're not attracted anywhere. Now you can imagine if you just deform the table a little bit, it might have a little trough, and that trough then makes it an attractor, or could have a little maximum, and then it will be repulsive. Cannot see the slides. Did I not share the slides? That's been a while ago. So let me make sure that you do. Okay. So there was some problem in the past, perhaps, then, I hope. Good. Yeah, so this is, sometimes physicists call this marginally stable. So it's not really asymptotically stable. This will be also something that we'll have a lot. It's for interesting reasons. Okay, that's linear systems. When you have multiple dimensions, you need to generalize. It's not the slope. You have to generalize that a little bit. I'll not explain that really. Those of you who had linear algebra might remember that in a multidimensional system, the equation becomes a vector equation, and the linear coefficient there in front is a matrix, and that matrix can be diagonalized, and the real parts, they have eigenvalues, and okay, the real part, I have eigenvalues, and it's the real part of the eigenvalues that determines stability. If the real part of the eigenvalues is negative, then you have a stable, asymptotically stable state, and this has to be true for all eigenvalues, then it's an attractor. And if there's a single eigenvalue where the real part is negative, then you have an unstable fixed point. It's an unstable direction. If there is a real part of any eigenvalue that is zero, then you have a marginal stable property in that direction. So technically, it's no longer asymptotically stable. So if you don't know what eigenvalues are and so on, then this is not, you don't have to learn it here. But that's, of course, the more general embedding of this. Now, in nonlinear systems, you can actually use the so-called linear stability theorem. So nonlinear dynamical systems are characterized by the stability of the linear approximation. So if you're linearizing the system around the fixed point, now stability is really a property of the fixed point, right? Engineers sometimes say the system is stable or the system is unstable. And that's because they're thinking of an essentially linear systems, and the linear system has only one fixed point, right? The linear function only intersects once at the x-axis. And so then there's some people say, well, the fixed point is stable, that's the same as the system is stable. But if you think about a nonlinear system that can have multiple fixed points, and we'll look at that in a moment, then it's clear that the stability is a property of the fixed point. So it's not the system as a whole, it's each fixed point. And so what you do is around every fixed point, you linearize the equation. I'll not explain exactly how. Something that, that where the slope in multiple dimensions is approximated by that linear function. And then you can use the linearization to decide the stability. So if the eigenvalues of the linearization are all negative, the real parts are all negative, then you have a stable fixed point. If there's any positive real part, you have an unstable. And if there's any zero a real part, then it's actually undecided. But then the linearity does not decide that. And that's sort of an advanced point. It's sometimes called a non-hyperbolic fixed point. So here's an example. I'm just making a 1D example of some, and say that's maybe one direction of one eigendirection, one eigenvector. And so here would be an example where this is the nonlinear system, that's the linear approximation, negative slope. So in that direction will be stable. Again, this is the nonlinear direct system. The black one is the linearization, positive slope, that will be an unstable system. And this would be 4 examples of a linear approximation being zero, having zero slope, and the red line, the nonlinear system, having different behavior. So you have 4 possible cases. You could have something that ultimately goes like a positive slope, ultimately goes like a negative slope, or has these convex or concave shapes. And you see that different things would happen. You could imagine that if you have this here on the top right, it might still be stable. I drew this by hand, but if you look very, very closely, the rate of change will be negative to the right and positive to the left. So this mental simulation would still argue for this to be a fixed point and then this to be a repeller. But if you have a situation like this, for instance, that would mean that, yes, you get attracted here from the right because the rate of change is negative here, but you would get repelled on the left. So it's like a halfway attractor, if you wish. And the analogous thing with mirrored would be the case here. So for these sort of so-called non-hyperbolic fixed points, you need to make a more detailed analysis. And this does happen near bifurcation, so that's why it's relevant. Okay, now gets even worse. But this is maybe the worst this will be the hardest part. Bifurcations. So bifurcations are changes in the stability and or number or the solutions themselves. So the stability of fixed points. And one can define this more generally. So what does it mean, changes? And so here we're looking then at families of dynamical systems. So we vary something about that dynamical system. Usually we think of that as some parameters that you have, some parameters in the equation. As you vary the parameters, the equation changes, the curve, the f of x, right? The f of x is deformed mathematically. You can imagine later when we're looking at our neural dynamical models, the inputs will be such parameters. You apply an input and you can continuously vary the input, for instance, strengthen the input or decrease the input strength, or you strengthen its structure, its shape. then as you do that change, the dynamical system changes because input is part of the dynamical system. And then we're interested in what happens to the solutions. And so generally, we're looking at parameters which that the dynamical system accepts, that is the equation itself depends smoothly on these parameters, right? If you have a parameter where suddenly when you change the parameter a little bit, the equation jumps to some new value, you can imagine then things are not well defined and so on. That doesn't occur. And where if you think of inputs, they're always, we think of them as changing smoothly. Like you can increase the strength of an input in a graded way, not in a jumpy way. And so what we're asking then, if there is a smooth change of parameter, is it possible that some of the solutions sometimes change smoothly and sometimes change abruptly? So when they change smoothly, then we again have this notion of topological equivalence, that is, the dynamical system at the change value is different in detail, but it isn't, you could sort of map it onto the solutions that you had when you had the previous value of the parameter. So again, think of it, the solutions being on some rubber surface, and then you could sort of distort the rubber a little bit to map the solutions across the different values of the parameter. Bifurcation will occur when that is no longer the case. That is, now as you change the parameter just a little bit, there could be a jump that now the solutions are no longer topologically equivalent. To map them onto the solutions at the neighboring parameter value, you would have to cut the rubber band and glue it back together in some other way. So let's make this concrete. So here's a family of dynamical systems. I'm using the saturation of the red here to indicate different states of the dynamical system when parameter values from the saturated red here on top to these light forms, and it will be continuously deformed that way. And let's start here with the bottom shading here. This will be a nonlinear dynamical system that has three fixed points. Here is a negative slope fixed point, that's an attractor. Here is a positive slope fixed point, that's a repeller. And here is another attractor with a negative slope. And now I'm changing the parameter that ultimately lifts up here the left bottom, adding some, like you can think of adding a linear function if increasing slope to this that goes through this. So this fixed point hardly moves at all, but here these move. And as you lift this up, the repeller and the retractor approach each other, and then at some critical point they will maybe touch. The line will be just tangent to this line, and then it will lift up and go. And there is no longer a fixed point or neither repeller nor attractor left. So locally around this would be called a bifurcation. So it's a qualitative change of the dynamics, and this change in the number, nature, or stability of fixed points as the dynamics changes smoothly, again, with the assumption that the shading here would be continuous as I change the parameter. And so this particular bifurcation is the so-called simplest bifurcation. It's called tangent bifurcation. Now, for obvious reasons, I think I have a better plot of that in a moment. Yeah, we'll get to that. It's called the tangent bifurcation, and that's when two fixed points collide, a repeller and an attractor, and they annihilate in the sense after the bifurcation has occurred, there is no more fixed point here. Mathematically speaking, those who know that kind of stuff, it's a bifurcation that has codimension 0. That's why it's called simple. So again, it's a local bifurcation. That is, we're talking about this environment. The fact that there's no other attractor here around, that's a non-local. Local in this sense of infinitesimal, if you go to the point where this exactly happens, where this is exactly tangent, and the repeller and attractor are exactly coinciding, an infinitesimal interval in state space around X and infinitesimal interval in this parameter. In that environment, we're looking. In practice, it's going to be finite size, but mathematically speaking, would be just local. And that's generally true. All the bifurcations we look at are local in that sense. So if there's an attractor at some finite distance, that's a separate story. That isn't really characterized by the bifurcation. And that will be typically true in our neurodynamic models as well. Yeah, you can think of the same bifurcation run through just in the opposite direction. Right here, I'm suggesting I just change the color so that the light values are on top and the dark ones on bottom. So you can either think of this having been run through in the direction from dark to as previously from this bottom plot to the top plot, or from the top plot to the bottom plot. And that is true for all bifurcations. There's always two ways in which you can run through them. I'll make this tangent bifurcation the example around which we understand that a little bit more precisely. And so again, bifurcation is qualitative change of the dynamics. And it turns out that this qualitative change is induced by an instability. So bifurcations and instability are sort of the same thing. And instability really means that an attractor becomes unstable. So attractor is a stable solution, asymptotic stable, and becomes unstable. And that's here in this case, the attractor becomes unstable as it disappears, just at the moment when it disappears. And more generally, we'll look at a couple other examples where it doesn't always have to disappear, but where it becomes where the attractor changes property. For instance, its real part becomes zero, for instance. That's where the bifurcation occurs. And so here in this case, here's a more local form. That's sometimes called the normal form. This is the polynomial equation with the smallest number of terms that has that bifurcation. So that's just a negative parabola. These are negative parabolas, and you add a constant. And when that constant is zero, that's exactly when you get this negative parabola minus x squared that you might all be familiar with. And there you see it's just tangent. So there's a fixed point, and it's one of those funny fixed points that is the linear approximation, which doesn't determine the future. Like there's a negative slope here on the right, so it would be attracted in here, but there's a negative slope also on the left. No, sorry, a positive slope on the left. So, negative values on the right would be attracting, and negative values on the left, so that would be repulsive, right? If you're, and these values would further decrease x, so move away from this solution. So when alpha is negative, you would really have no fixed point. And when alpha is positive, then you have two fixed points. Here is a stable one, negative slope, and here is an unstable one, positive slope, right? And you could plot this here by looking at the fixed point as a function of alpha. For negative alpha, there is no fixed point. And for positive alpha, there is that stable fixed point here at positive values, and that blue unstable fixed point at negative values. If you figure this out, I'll give you an exercise exactly around that. You can figure that out. Then it turns out it's a square root of that alpha. That's why I plot these functions. You see the square root makes that these two meet here with infinite slope. They hit each other here and then disappear. That's the tangent bifurcation. And the slope becomes zero. See, the slope is negative, and then the slope really goes all the way to zero. That's how you see that stability is lost. So it turns out that there are only 4 simple bifurcations. And we will be working with these 4 bifurcations all along. Actually, only 3 of those are really relevant for us. That is due to a theorem. We know that a theorem that someone called Edward Hopf proved in the 30s, I think early 1930s. It technically speaking says that if you have a fixed point such that a single eigenvalue, and for some reason there can be sometimes a pair of complex conjugate eigenvalues, forget about that, crosses the imaginary axis, that means the real part changes sign, then only one of these 4 things can be the case. And the one that I just looked at is called the tangent bifurcation. I'll briefly flash here these other 2 and then say a little bit about the 4th one, the Hopf bifurcation. So one of these 4 things happen. So the transcritical is described by that mathematical form, and it's an equation. You could think of this like a rubber band again, and you pull this down here on the left, and as you pull it down, you shift the rubber band. And so at the critical point, it's also just tangent, and then it goes up again on the other side, and that will make that the slope goes through zero, so that's where it's unstable, but the fixed point moves continuously. So for these leftmost values, you have a positive slope here and a negative slope, a zero. So that will be a stable solution at 0, right? The negative slope is here, and an unstable solution at negative value. So this is an unstable solution here. And then they are colliding here at 0. And then after the switch, the positive slope stays at 0 and is now unstable. And then at the positive half, you have a negative slope, so that's stable. So we don't use this typically. It's conceptually important to realize that there can be bifurcations where it looks like nothing happens. Because if you look at the stable state, stable state is actually continuous. It goes, this corner here, but it's no jump. So the stable state will go and then increase this way. But still, there is you don't in practice really see the unstable state, right? If you have a system that has an unstable state, some noise will make that you always go away from that unstable state. So you'll only observe the stable state. And so you can have that a variable changes smoothly as a parameter is changed, but there is still an instability somewhere. And you would notice that in that there would be less resistance to perturbations and to noise, and you would get some unstable behavior around that parameter value. So that is a warning that you can say that it always has to be some jump and some switch to say that it's a bifurcation. So that's a transcritical one. The pitchfork is a bifurcation that's relevant when you have some symmetry property. So this is its normal form. These were drawn by hand. The x to the third is this sort of function. You might be familiar with that. You have negative, then it becomes flat here, and then it goes down this way. If you add a linear function to that, the linear function either makes that it goes really very smoothly through here if alpha is negative, or that there is this inversion, this curve here. This will mean that if you have very small x, this term will be dominant x to the third for a very small value is a very small number, so it's mostly this here. So around 0, it's more like this axiom. Then when alpha is positive, it's a positive slope. And if you move to larger x, then this becomes the dominant term, and that means it has this function which goes negative for very large x and positive for very small x. And so it has 3 fixed points, right? One here, one there, and one here. And so this is what it looks like. Again, it turns out to be a square root of this parameter value, and you will have a stable state, this negative slope, that collides with another stable state. In the middle is an unstable state, and when they collide, then a stable state remains in this case. So that's what pitchfork, you can see why pitchfork, right? This looks like if you think of this fork, this would be the handle of the fork, and these are the 3 prongs. It's like a hay. In German, they call it Heugabel bifurcation because it has like a pitchfork which you use to move hay. There's also a reverse. The same kind of solution exists when you switch the stable and unstable. So switch the blue and the red just by letting time go backwards with a minus overall here, and so that can be a case where this would be stable here and everything's unstable, so that a stable state would just disappear. Similar in the tangent bifurcation, it's just gone, and then you switch somewhere else. So you can see this is a special case where, for symmetry reasons, 3 things meet at the same time. Think of 3 people here. These are 3 people who meet. And in the real world, when 3 people meet, it's always going to be 2 people who meet first, and then the third one joins. And you have to have something very special that all meet exactly at the same time. Right? They would have to sort of the rate of approach would have to be synchronized, and that would be true due to some symmetry. There's some symmetrical reason that forces the 3 solutions to collide at the same point. If 2 collide first, that will be a tangent bifurcation, and the third solution would just go through. So because sometimes there are these symmetry properties, we do sometimes get these pitchfork bifurcations. This is more relevant to the summer semester, where we use this to analyze the dynamics of path generation, where this is sort of the limit case where you're colliding with an obstacle exactly symmetrically. In the nonlinear dynamics, we don't really have pitchfork bifurcations, I think. Yeah, lastly, the Hopf bifurcation, for which we need high dimensions, and actually discuss this for two reasons. One, it's actually they're really occurring in neurodynamics, and it illustrates the idea of vector field. So just introduce that briefly. The vector field is very intuitive if you look at two variables, x1, x2. A dynamical system of two variables means the rate of change of one variable depends on both variables, and the rate of change of the other variable depends on both values, and it could be different functions. So the fact that x2 shows up in the equation for x1 is a form of coupling. If x1 shows up in the equation for x2, that's a reciprocal coupling, and we'll be looking at cases like that later. So the vector field notion is quite intuitive. That is, for any initial pair of values, x1 and x2, the future is uniquely determined. You could say that these rates of change are little vectors that show in which direction you're moving. So for instance, here, if at every point I plot a vector, has the same dimension, f1 and f2 have the same dimension as the underlying space, x1, x2. So I can just plot a little vector where the x1 component is x1 dot and the x2 component is the x2 dot. Get these black vectors, and they are all tangent to solutions. So you can almost kind of see the solutions by just following the vector. So for instance, this initial condition, you would be just converging to this fixed point. So actually, generally, in high dimensions, a dynamical system is exactly this vector field. That is this function that maps the original space into a space of the same dimensions. That's the rate of change. And that's a mapping from one space to the same space. That's called a vector field. A field of, think of the original space as spanning a field, then it maps on the field of the same dimension. And so fixed point attractors will all transfer to that. And the Hopf bifurcation, again, is a bifurcation in which there is a stable fixed point that becomes unstable. And what happens is that then an oscillation arises once the stable fixed point disappears. Here's a special ways of how one can look at that. You can have a pitchfork bifurcation for the radius, and you have a constant rate of change for the angle variable. So it's actually takes two dimensions. It's based on having a pair of eigenvalues that change, complex conjugate pair, for those who know these kind of things. And then you can use polar coordinates to represent it in that way. And then along this radius, you would have just one half of the pitchfork that is negative slope that becomes 0 and then becomes a positive slope. And then there's a new attractor here at a finite radius, while the angular variable is just has a constant. It's like this linear increase in walking distance I mentioned initially. Now you have that for phase. And if you reassemble the xy representation, I seem to have deleted the equation for that. So x would be really just r times sinus phi, and y would be r times cosinus phi. So these polar coordinates transformed into x and y again. Then you can see that the solutions would be, r, the amplitude, times sinus omega t, and the solution of this is omega t, and the other one is cosine omega t, so it makes an oscillation. These details you don't really need here. We will be looking at oscillatory solutions like that at one point in the lectures, but only it's like a small part. I just want to make sure you have that whole landscape. Okay, so this is the most complicated it ever gets. Don't worry, you don't need the details of this. I'm very close to closing this more difficult part. I'll just now tell you why I do even do that. Why I have this bizarre bifurcation qualitative theory and so on. And that has to do with forward versus inverse dynamics. So what you learn in calculus courses and in a lot of the continuous mathematics courses for computer science and for other engineering and so on is what we call forward dynamics. That is, you know the equation somehow, It's from a law of physics, some model that you make, and you're just trying to solve it. So from the equation and maybe some estimates of the parameter values, you determine solutions numerically or analytically. And if you use qualitative dynamics, you would determine the fixed point, and I'll give you an exercise where you can do that, and maybe limit cycles and other things in their stability. And when you want to qualify, when you do qualitative dynamics, what you want to do is characterize the ensemble of solutions. For instance, if you know there's a single fixed point, it's attractive, then you know the whole flow, you know, from any initial condition, I will be converging that. If you know that there's a bifurcation and or there's some unstable state, then you can say, well, on one that unstable state might make a boundary, and on one side of that boundary, I'll converge one attractor, on the other side, I'll converge the other attractor. And in that way, you determine the entire set of solutions. And there's a lot of other things that you can do. For instance, something called standard manifolds. And now inverse dynamics is the problem that we are more often faced with in neuroscience modeling, or modeling of behavior, because we don't know what the fundamental equations of the brain are, right, or that describe behavior. What we do know are some properties of neural activation or of the behavior which we represent neurally by a neural network, and then we have some kind of description of what kind of neural states must be the basis of the behavior. And what we now need to do is find a dynamic system, an equation that has these kinds of solutions, or solutions with these properties. So we need to find the equation given the solutions. That's called inverse dynamics. That's a problem that's also faced when you build a robot with our techniques. In some sense, we talk about that. When you build a robot where you want to find the equation so that the solution of the equation generate the robot behavior you want. So you have some idea what kind of behavior you want, and then you need to have the equation that does that. And so that's the general model problem of modeling, writing down a model so that the solutions have certain desired properties. Desired even either because you design an agent that has some goals, certain functions, or because you have data and you want to explain the data in the model. And that's where we're using the bifurcation theory. Essentially, the notion is that sorry, I got some layout here of the slide is a bit odd. And so you have some constraints from experiment, and we're framing these constraints as being informative about stable states, because we'll be postulating that neural states that are significant have stability properties, so they've got to be attractors. So we know there's some attractors, and maybe we also know as we change input or some conditions, the attractors will maybe disappear at some point, or there's an instability at some point. And then we can say, well, if we use these bifurcation theorems, we can say what class of bifurcation that is, and therefore in which of the four elementary pictures we are, and we can write down representative of the class of that bifurcation to do the model. So we don't literally do that in this course because we're actually also constrained by some other thoughts about the class of equations, but we do this in a certain sense, and you will get an experience for that sense. So we'll be looking at certain kind of instabilities. We call this detection, selection, memory instability. And we will characterize these stabilities as bifurcations, that is, what attractor existed before and what attractor exists after bifurcation. And then we'll design the dynamic system, or essentially design the input-output functions around these particular bifurcations. Now, this is all very abstract. When we do this more concretely, it will be understandable in much more concrete ways. But this is sort of the mathematical embedding. So the thing that we will really need and that you will understand concretely is the notion of fixed point attractors as stable states, and then them becoming unstable, and this the instability being a form of bifurcation, and which particular bifurcation it is, what the other solutions are that we'll be looking at, bistability and things like that. That will be the concrete stuff we'll be using in the equations. So then you will really understand in the concrete context what these different terms mean. Yeah, that's maybe as far as I want to take this here.